Thanks. Today I'm going to talk about a paper that I wrote back while I was still a postdoc with a student at Stanford named Caleb Cook. Our paper, you can find it on arXiv. It's been published, but okay. Morally, I feel like I should give you this sort of neutral number. Okay. Maybe before I talk about sort of what we did in particular, I'll try to briefly motivate thinking about hydrodynamics of electrons as a sort of interesting problem in solid-state physics. In some sense, the goal that we're after is not really hydrodynamics per se, but really a better understanding of the transport properties and of dynamical properties more generally in interacting solids. So, microscopically, right, we're studying many-body quantum systems, and they have a Hamiltonian which is kind of obnoxious. It has a lot of different terms in it microscopically. These terms in black are sort of non-interacting physics. So let's say we have some electrons, and they have kinetic energy as they hop through the lattice. So that's this H electron. The lattice itself could be vibrating. That's H phonon. We might have some impurities for either electrons or phonons to scatter off of. That's this H impurity. And if this was all that we had, this would be a non-interacting problem, and it could be exactly solved. However, in the real world, we also have these interacting terms in red. So we have electron-electron interactions, electron-phonon interactions. I ran out of space, but there's also the phonon-phonon interaction term. And in general, this ruins the solvability of the problem. Now, in an ordinary metal, this is not such a severe issue because Landau taught us that these interactions are, in a modern sense, irrelevant. So for most practical metals, it's sort of OK to go ahead and treat this term as a perturbation to these kinetic terms. But as a formal question, we might ask, what if these interacting terms were not small, not only sort of at the microscopic level, but what if in the sort of effective description at low energies, at room temperature, what if these terms are not perturbative? What if the interactions really are important? And I'd like to emphasize that much of what we know how to do in solid-state physics takes a flavor of essentially starting from this Hamiltonian and then weakly adding whatever interaction is hard to deal with, and then just doing perturbation theory. But we'd like to understand if there's anything that we can say that's really non-perturbative. Okay. Now, in particular, if we're interested in understanding transport physics, what's the resistivity of a metal, what's the finite frequency response, these questions are not computationally tractable in their complete generality. Okay? So if we look at this problem and we just say, this is too hard to solve by hand, but why not just put this on a computer? Okay, there are a number of reasons why for let's say, just to calculate the DC resistivity of a metal, you can't put that on a computer. You won't get a sensible, or at least a controlled answer. So let's start with an obvious point. So the Hilbert space of a many-body system is exponentially large. So any sort of exact method is sort of silly in a 2- or 3-dimensional system. Many of these problems, the one sort of approach that you might not think is sort of manifestly ridiculous would be to do something like, let's say, quantum Monte Carlo. This often suffers from what would be called a fermion sign problem. Let me not go into that, but say that in sort of generality, this problem is probably not tractable. But there may be some special toy models that are tractable with quantum Monte Carlo. That's great. That will give you thermodynamic properties. It will tell you maybe what the ground state of your system is. But it doesn't actually give you the resistivity because quantum Monte Carlo gives you imaginary time data. And then you have to analytically continue this into real time. This is only mathematically well posed if you have every single imaginary time data point exactly known. The moment when you have to truncate this sequence and there's errors, this becomes numerically somewhat ill-posed. And so, for very simple experimentally measurable things like resistivity, we're sort of screwed, okay, in generality. So this is the sort of background to which we're entering with our story about hydrodynamics. Maybe the last point that I should mention is just that this is not some sort of story that we tell theory students that has no relevance to the real world, because real systems are hard, or can be hard, okay? So this scenario that I mentioned here, where we have sort of interactions, we have kinetic energy, everything is on an equal footing, this scenario can really arise in an experiment, okay? So this is a more or less random example of a zoo of materials that I've picked from with very complicated phase diagrams. This bright orange fan that you see labeled non-Fermi liquid is going to be a regime where this sort of problem arises, okay? All right. Now you might say, okay, it's true that microscopically this is a very complicated system and we can't solve it exactly, but in many ways, you know, the ancients also had to deal with this same problem. So back in 1800, people were trying to understand the dynamics of liquids and gases. These are systems with 10 to the 24, 10 to the 28, I suppose, depending on the scale you're interested in, particles. Certainly not exactly solvable, even on a modern computer. And nevertheless, they more or less solved this problem. Okay. And how did they do it? Well, they didn't talk about the microscopic dynamics of every single degree of freedom in the system. Rather, they said that out of this complicated microscopic zoo of moving molecules and collisions, some simple effective description called hydrodynamics would arise. Okay? In the physics language, hydrodynamics will be an effective theory governing the relaxation of your perturbed fluid to thermal equilibrium. Hydrodynamics is valid on long time and length scales. And in particular, what we mean by long is that we can talk about hydrodynamic phenomena on long time scales compared to microscopic collision times between the molecules in our gas. And we can talk about hydrodynamics on long length scales compared to a mean free path between collisions in the gas. Okay? And I've already here written EE for this collision time because for this talk we'll be replacing the molecules in air with the electrons in a metal. Okay? And so you might say, well, why not just apply this same story, and now we've solved our dynamics problem as well. Okay. There's a sense in which you can do this and you can solve this problem, and here's the answer. So the degrees of freedom in a hydrodynamic theory correspond to quantities that are locally conserved. They are the slow modes of the system. Everything else will just relax away. You can't see it anymore. And in a typical solid, we can think of two conserved quantities. Okay? We have the local charge, because electrons can't be created or destroyed, well, at least at these energies. And we also have energy. Okay? And so the hydrodynamic theory that couples energy density and charge density, if we ignore this issue of Coulomb interactions, okay for what I'm talking about today. But if we ignore this sort of irritating issue for a metal, the hydrodynamic theory that would couple an energy density to a charge density is this diffusion equation. Okay? And the most exciting thing about this equation is that there's a 2x2 matrix. So probably not very exciting to a mathematical audience, but that's about all we get. Now, these equations are even less exciting when we realize that if we're interested in, let's say, the DC resistivity of our system, we can cross out this side of the equation. And what we end up with is nothing more than the local form of Ohm's law. And all we've learned is that electrical and thermal transport might be coupled. Okay? And this is not a new fact. Okay. So the situation might seem a little strange. You might ask, why did we not recover, let's say, the Navier-Stokes equations like the classical gas? The problem is that in a metal, these electrons that are moving around are not momentum. They don't have a conserved momentum. Okay? They'll never have an exactly conserved momentum because a metal always has a microscopic lattice that has broken translational invariance, and also we can have a lot of disorder, and that's in some sense an even more severe effect. And all of and both disorder and essentially Umlauf processes off of the lattice will break momentum conservation, and this is why we get this sort of very different hydrodynamics in an ordinary metal. the way we can think, at least cartoonishly, about the ordinary metal is that we start with this one lonely electron in blue, and it sees a zoo of impurities and Umklapp processes, and it just sort of bounces, from one impurity to the next. And you can think of, pinballs in a pinball machine. Okay, this is effectively, a system with no momentum conservation. In an ordinary metal, it's essentially a single electron, described by kinetic theory, moving around in this zoo of impurities. Now, our hope is that one day we'll understand the non-Fermi liquid as perhaps the following scenario. So we take the same metal, it's kind of dirty, but when we're in this non-Fermi liquid regime, interactions have become quite strong, and the interactions between our particles may be so strong that even though we have all of this disorder, there's still sufficient interactions between these big blue blobs that they might begin to exhibit some collective phenomena even in this dirty background. And there's, I would say, no experimental evidence that I know of for this scenario. It's a bit of a dream at the moment. It's not completely crazy in the sense that we don't really have another generic description for such a system. So it's either sort of this or nothing, at least in a general sense. Yes?
So when you say it's non-Fermi liquid, you mean you can treat it as the electrons of actual particles interacting directly?
Well, this is a cartoon. I mean, in practice, one would not want to do that, but I just, all I want to get across here is the notion that perhaps some of these strongly interacting systems have such strong interactions that even though they're kind of dirty, it's not fatal. Okay. All right. So today we're going to talk about the following scenario. This is a much more controlled scenario, if a little less exciting, which is to take a good metal, which is described by Landau's Fermi liquid theory. It will have long-lived quasi-particles. Okay? However, we're going to try to take out all of the disorder, or as much of it as we can. And in this regime, even though we have these weakly interacting objects, we can think of them as forming some semi-classical gas. Okay? There won't be a lot of impurities for them to scatter off of. And so in this system, momentum might be a parametrically long-lived quantity, and so it may be sensible to just ignore this one impurity. Okay? The dynamical properties of this system may be controlled entirely by an effectively momentum-conserving gas. Okay, so now let me ask, if we had this classical gas of quasi-particles in a metal, what would we find? So, experimentally, we don't have access to quite as many things as we do if we're, in a mechanical engineering lab studying fluids. So what can we look for in a solid? Actually, it turns out there's a very simple fluid flow that gives quite striking predictions for experimental systems. Okay, this is a French name. In solid-state physics, we call this Girja flow. It corresponds to taking a two-dimensional, essentially channel of fluid. So I'll have in mind here 2D or quasi-2D materials, but you could do a 3D analog of this if you wanted. And we'll take this channel to be relatively narrow. Okay, it has width W, but otherwise homogeneous for simplicity. And then we're going to apply an electric field down here, and that electric field will drive an electric current through the channel. Okay? And our question is, what is the resistance per unit length of this device? Okay? So, in theory land, we plug this channel into our ohmmeter and we just read the dial. Okay? That's what we're after. It's most natural to talk about the resistance per unit length of this device. And this resistance per unit length will scale as 1 over the width of the device, roughly speaking. You can think of this as a parallel resistors effect. The wider that the device is, the more ways that the current could flow in parallel to one another, so the resistance will go down. And then there's a factor of 1 over tau. And in an ordinary ohmic metal, this 1 over tau would be a constant. This constant is telling us that in the bulk of this device, the current, and to be a little precise here, the momentum that overlaps with that current is getting scattered by lots of impurities in the bulk. This limits how effectively current can flow in the metal, and this is really your textbook formula. Okay? So resistance per unit length is 1 over width times a constant. That constant is set by the momentum relaxation time. Now, if we're in this hydrodynamic regime that I mentioned on the previous slide, where the impurities can basically be ignored, but if we still have a lot of interactions between these electrons, then this momentum relaxation time will no longer be a constant, but it will be set by the device geometry. What has to happen, essentially, is that a hydrodynamic collective mode in this channel has to relax away. And the time that it takes for that to happen is governed by this diffusive scaling. Okay? So this object, 1 over w squared, times a diffusion constant for momentum, proportional in particular to the mean free path of collisions. Okay? This is the time scale for the decay of viscous modes. And if we plug in the facts that we know about metals, we expect that, more or less, this LEE could scale as 1 over t squared, where t is temperature. Okay? So at low temperatures, this resistance will become very large. And it will also scale as 1 over width cubed. Okay? So 1 over w coming from here, 1 over w squared from here. And these are both very striking predictions for experiments because we can create channels of different width. We measure 2 very different power laws here. In principle, this should be quite distinguishable. And we also measure this very unusual 1 over temperature squared dependence in a Fermi liquid. I don't think it's ever been seen, but in principle would be a very dramatic confirmation. Okay? All right. Now, one more problem that we have to deal with is that in a real metal, it may be difficult to get a device that's much narrower than the scale over which impurities scatter our electrons, but that's very short compared to the scale over which the electrons are scattering off of themselves. So we may also need to worry about what I'll call the ballistic limit. This will be when the channel is just very small compared to the mean free path for collisions between the electrons themselves. In this regime, what essentially happens is that the electrons in the channel are just sort of undergoing single particle motion. They bounce from one wall to the next. And if the wall is sort of rough and we don't sort of perfectly scatter and reflect off of the boundaries in every collision, the resistance per unit length of this device will scale as 1 over w squared, essentially because the momentum relaxation rate is just the collision rate at the boundary. So how long does it take to get from this boundary to this one? That will be w divided by our Fermi velocity. This gives us this 1 over w squared scaling. Okay? So 3 different experimental predictions just in this sort of simplest geometry.
So can I ask, so
yeah.
the t squared comes from the mean free path, or where's that coming from?
That's coming from LEE.
Yeah, okay.
Yeah.
So that's...
yeah, I mean, this is a classic result in Landau's that essentially the phase space allowed for 2-body collisions would scale as t squared. Okay, so now on to the hexagon in the title of my talk. So there was an experiment that looked at, or looked for this Girja effect in this material, palladium cobaltate. And okay, maybe these pictures mean more to you than they do to me. This material, as far as I'm concerned, is interesting from a theory perspective because it's not a sort of simple isotropic gas. Okay, this is the Fermi surface of the palladium cobaltate. It's a cylindrical hexagon. Okay, and this is approximately a 2-dimensional material, even though this crystal is certainly 3-dimensional. At least, hopefully, the image is clear enough to depict that. Okay, so we have this sort of cylinder. Most of the interesting dynamics will be taking place, in the direction of the hexagon. And just one more image to convince you. So this was probably some sort of a first principles type calculation, and this is an ARPES image, so a real experiment. Okay, went and imaged that the Fermi surface of this material is a big hexagon. Okay, and
the material that the full is that multiple layers that we're looking at? Is that
this is the whole crystal has this Fermi surface, and they'll generally try to not grow something this big. It will generally be thin, but yeah, I mean it is approximately 2-dimensional, and as far as I think we can tell, all of the interesting electronic dynamics, well, that I'll talk about at least, is effectively.
It's thin enough that it actually acts like a 2D material. Is that
yes. But I just want to say, that's not only a question of how they cut the material. It's also that this Fermi surface, right, is very slowly varying in the third dimension, and so all the dynamics will be very slow. Okay. All right. So there was an experiment done about 4 or 5 years ago, and they thought that they had seen at least the onset of this Girja effect in palladium cobaltate. So to be a little more specific, so this is the first time of 2 that I will change a bit of the notation, so I'm sorry. Experimentalists like to talk not in terms of a resistance per unit length, but in terms of a resistivity. I think this is not, I don't like this, but this is just what the community does. So basically, this just multiplies the resistance per unit length by W, but I do want to emphasize this is not a bulk resistivity. It critically depends on the geometry, okay? So what they're doing is they're plotting this versus 1 over W. Now, if we go back a few slides, we can ask, what do we predict? Okay? And we would predict that rho is 1 over W. It's linear if you have ballistic transport, and is 1 over W squared if you have viscous hydrodynamic flow. Okay? And it's also a constant, I should add, if you have ordinary ohmic flow. Okay? So this was the data that they got, and they argued that it looked more like the red curve, which is sort of a little bit of this W to the minus 2, roughly speaking. And it looked less like the blue curve, which would have been sort of mostly ballistic with a little bit of ohmic effects thrown in. Okay? It's not a very strong signal, though, but this is what they had. Okay. Now, they didn't talk about the temperature dependence. We'll talk about why in the end of the talk. And this is the data that they had. And we wanted to understand, did this experiment make sense? Okay. Now, the reason why it's worth asking this question is that the model that they used to predict the onset of hydrodynamic flow in this system, and looking at this image, we're definitely only seeing the onset of viscous effects. This is by no means a compelling W to the minus 2. So we really need to have, let's say, a full, at least kinetic theory model of what's going on here. The model that they used was for the kinetic theory on a circular Fermi surface. But we all know, probably from kindergarten onwards, that these two shapes are different. Okay? So the circle and the hexagon are different shapes. And so you might ask, whether this effect matters or not. If cows are spherical or not in the real world. So, okay, we can give a slightly more sophisticated answer. So what's different about a circle versus a hexagon? So an obvious thing, stated in maybe a slightly more sophisticated way, would be that the circle has a higher symmetry group than the hexagon. Okay? So for what I can stomach, the circle has symmetry group O2. The hexagon has symmetry group D12. So D12 actually is kind of a big symmetry group in 2 dimensions, but we could ask, is it big enough that it doesn't do anything to fluid dynamics? We'll resolve that question shortly. Okay. There's a less obvious effect that I'd like to mention quickly, which is that when we talk about the fluid dynamics on this hexagon and the onset of fluid dynamics on this hexagon, there's actually a hierarchy of scattering times that will arise. Okay? So the ballistic to hydrodynamic crossover is going to be much more complicated with this sort of Fermi surface than with a circle. Let me quickly mention why that's true. If you want more, you can read the paper. So suppose that we're this electron on the top right of the Fermi surface, and we want to scatter in a 2-body collision that conserves energy and momentum. So conservation of energy means we need to scatter somewhere else on the Fermi surface, and conservation of momentum means that whatever momentum we exchange has to be compensated by an opposite exchange by another pair. Okay, so if we're in this top right corner, one place that we could scatter is off of this other electron in the top left corner. And this is a nice scattering process because there are a lot of them. Okay? What's basically happening is that we can take this electron and we can just slide it anywhere we want along the top branch of the Fermi surface. And there's a huge phase space for these collisions. Okay? This will be a fast scattering process, this sort of inter-side of the hexagon relaxation. The slow dynamics in this problem corresponds to taking this electron and trying to move it onto another side of the hexagon, okay? Because there's only one place, essentially, that we can compensate for this. And that corresponds to its mirror collision, okay, on the other side of the hexagon. So if we imagine that this hexagon isn't perfectly flat, that gives you some sort of trivial infinities, but we assume that it's sort of a nearly flat hexagon, we find that the scattering rate, the separation in scales, let's say, between the scattering rates on a branch versus off of a branch is essentially set by some relative radius of curvatures on this hexagon. And I think this is at least an order of magnitude effect in palladium cobaltate, but I don't remember the exact number. Okay. I should also mention there's yet another scattering time, which was pointed out by a group at MIT. You can already kind of see it. It has to do with parity even versus odd modes. You'll note that this is sort of only an even relaxation mode. And let me not say anything about that, because that makes the story sort of even more obnoxious. OK. So you can read about, there's kind of a nice cartoon for a sort of intermediate hydrodynamics on timescales that are long compared to this scattering time, but short compared to this scattering time. But let me just sort of skip to the end of the story, which is what you would see if you were truly in the hydrodynamic limit for this material. Okay. So we started from kinetic theory. We calculated the hydrodynamic equations, at least in our sort of kinetic cartoon. This is the form of these hydrodynamic equations. We could have guessed these. We could have guessed these without going through the kinetic theory derivation, but this is what they are. This first term corresponds to the conservation of charge, okay? And this is just telling us that the number of excitations on the Fermi surface is constant as a function of time. Now, in an ordinary textbook on fluid mechanics, you would see this term and this term. The first term is, the first two terms, rather, form the usual continuity equation. And then what we found on the hexagon is there's one more term, okay, this minus d grad n. This is not an artifact of a sort of fluid frame. You cannot try to sort of get rid of this by a change of variables without introducing something that's just as just as strange appearing. Okay, so you're stuck with this term. Sean Hartnell calls this an incoherent diffusion constant. What it's arising from is the fact that exact or perhaps approximate Galilean invariance has been broken. Okay. We know it's broken because, remember, the symmetry group of the hexagon is not the same as the symmetry group of the circle. So we know from the moment we're talking about the hexagonal Fermi surface that we don't have an even approximate Galilean invariance to talk about. And as a consequence, it turns out the charge current and the momentum density become very different objects. Okay? What this diffusion term is telling us is that it's possible to have no momentum, no fluid velocity, okay, and yet still push a current through this device. Essentially, just because you can arrange your electrons on the Fermi surface such that they carry a current without momentum. Okay, it's one of the fun features of this anisotropic system. Probably the more subtle thing, which took us a while to understand, is that we get a new viscosity tensor. Okay, so in an ordinary fluid, you would have expected to see two terms. Although they would not have been the same two terms that I've written down here. In an ordinary fluid, you would have expected to see this term, which we would call shear viscosity. Okay? And then you would have expected to see a term called bulk viscosity, which would have been delta ij, delta kl. Okay? And these two terms you can understand essentially because if you look up in a book, let's say on elasticity theory, you think that you've got this fourth rank tensor, and you sort of crank through all the symmetries, and you find that there's two things you can write down. Okay? But in this fluid, we find this sort of unusual term. Here, epsilon is a Levi-Civita tensor. Okay? And what this term is telling us is that it's as if we have this model which is isotropic, and yet that we have these epsilons floating around. So maybe I'll come back to this on the next slide. Okay? We call this term rotational viscosity. I'll explain why shortly. And let me emphasize that this is a dissipative contribution. Okay? This is not the same thing as the Hall viscosity. there is an analog of this effect in liquid crystals, but I would argue that conceptually, this is really a unique phenomenon to these electron fluids in solids. Okay? So it's I think, quite a fun result.
Can I ask a question?
Yeah.
So let's just say I have just a bunch of particles, and I just do MD for a Hamiltonian that has a hexagonal kinetic energy.
Mm-hmm.
Yeah, what would I see?
You'll see all of these terms. Yeah.
So simple as that.
Yeah. Okay. So where is this coming from? The origin of rotational viscosity is the fact that the ionic lattice, which we've assumed to be frozen for the electronic degrees of freedom, which I think is perfectly sensible, this ionic lattice is frozen, okay? And as a consequence, the electrons see a world without rotation invariance, probably not surprising. But this actually has severe consequences, or important consequences, on hydrodynamics. The reason is as follows. So if we had rotational invariance, okay, then we would list out all of the conservation laws of our fluid. We would have, let's say, number density of fermions. We would have momentum. And we would also have angular momentum. Okay? Now, even in 2 dimensions, there's a sense in which this angular momentum symmetry is a non-abelian effect. Okay? It's a non-abelian symmetry. The generator of angular momentum does not commute with generators of momentum. Okay? What this means for hydrodynamics is that you can't both define a fluid velocity, essentially a density of momentum, along with a density of angular momentum. These cannot be independent degrees of freedom because classically the Poisson bracket doesn't vanish. Quantum mechanically, the commutator of these operators doesn't vanish. Okay? In fact, what the rotational symmetry does to your fluid is it adds a constraint. Okay? So it tells you that when you try to write down the equations of motion of your fluid, the knowledge of this additional symmetry will constrain what terms you're allowed to write down in your effective theory. And in particular, rotational invariance will give you that the stress tensor becomes symmetric. Okay? We don't have this symmetry on the hexagon, so we don't need to write down a rotationally invariant stress tensor. And if we go back, and we keep in mind that tau ij would be this eta tensor contracted with dk vl. Okay, this blue term is just dj tau ij. When we keep that in mind, we see that this rotational viscosity is precisely a term that broke rotational invariance. Okay? And physically, what this rotational viscosity will do is it will take a fluid configuration where the Fermi surface has been rotated, okay, and it will try to pull it back. That's what the rotational viscosity does. Let me just contrast this with the theory of elasticity, because I mentioned that earlier. So when we usually think about anisotropic systems, we would impose this symmetry, and this is not incorrect for a solid. Okay? The reason is that the ionic lattice has spontaneously broken rotational invariance. And you can think of this as the difference between a fluid that doesn't conserve charge and a superfluid. Okay? Both of them have broken charge symmetry, but only one of them was spontaneous. The superfluid spontaneously broke a symmetry, and that's why it still has memory of this symmetry in its hydrodynamic description. Here, because we're talking about this non-abelian effect, we don't have Goldstone bosons. We just have this symmetric stress tensor. OK. So that's the hydrodynamics of this system. So now let's ask, I told you this Girja effect before would be the simplest way that you could look for hydrodynamic effects in a solid. So let's now see what this does, or what the Girja effect looks like with a hexagonal Fermi surface. There's one effect that we immediately need to talk about, which is that the hexagon has broken rotational symmetry, and as a consequence, we also need to talk about the angle that our device, let's say the angle that our Fermi surface is making with the channel cut out through our device. If we solve the Boltzmann equation, which I won't really talk about, but this is the answer. If we solve the Boltzmann equation in this channel, okay, then as we increase the width of the device, okay, 1 over the resistance per unit length, so second change of notation, also called the conductance, okay, the conductance has this sort of funny behavior. At small widths, okay, this is when we're in the ballistic regime, there's basically no collisions at all. G is scaling as W squared, so that's why we've divided it by W squared. And this is equivalent to this resistance per unit length being 1 over W squared from before. Out here, this is G over W squared linear, or G scaling is W cubed. This is the viscous regime, okay? And this is also the same width dependence as you would have had with a circle. But I'd like to emphasize that with the hexagon, you get this sort of funny non-monotonicity that arises, okay? If you have a circular Fermi surface, what you'd see looks a lot like this purple curve. So you would start down here in the ballistic regime, you turn on momentum-conserving scattering, and the conductance just goes up. Once you include impurities, essentially the purple curve would just sort of cap off. Okay. Actually, I guess with this scaling, it would start to decrease, okay, as 1 over W. However, depending on the angle that this hexagon makes with the Fermi surface, we can get this dramatic non-monotonicity. Okay? And so this intuition that the Girja effect is associated with an increase in the conductance is wrong, okay, for a generic metal. So it's not too difficult to explain where this effect is coming from. So it's essentially a ballistic effect. Suppose that we really turn off all the interactions. We just have this hexagonal Fermi surface stuck in the middle of this channel. If the hexagon is offset relative to the channel walls, then essentially all the particles on this Fermi surface, which move normal to the Fermi surface, will bounce off the walls. Okay? And because all the particles, let's say in this idealized limit, have to sit on a side of the hexagon, they have to collide with the wall no matter where they go. However, if the hexagon is perfectly aligned with the channel, then the particles on the top and bottom side of the hexagon don't collide with the walls ever, and they can travel forever. Okay? And these contribute, if you were in perfect alignment, in infinite conductance, semi-classically. Okay? In the hydrodynamic limit, it turns out that the hexagon is symmetric enough that there's no angular dependence to the viscosity anymore, and so all of these curves have an identical slope, okay? And the slope is basically proportional to 1 over the sum of shear and rotational viscosity. Okay. All right, so in the last few minutes, let me return to this experiment. So now that I've told you all about this model, and I think its sort of fun features, I can tell you that it has nothing to do with palladium cobaltate. Okay? So I wasted a bit of your time, I suppose. Why is it not relevant? Well, it turns out that we asked, after we did all this work, we asked Andy McKenzie for his full data set so we could compare to it, and he gave it to us. And we replotted it the way that we would like to replot it. So this is what we did. Again, we're plotting conductance divided by W squared. So in the ballistic limit, that's why all of these curves, at low temperatures, this is the ballistic limit. Okay? At low temperatures, all of these curves are constant. That's G over W squared. Okay? As a function of temperature, we see that the conductance is always a monotonically decreasing function. Okay? So that's not fatal, because as we saw here, it would be possible to have a decreasing conductance as a function of temperature. But it's maybe a little bit surprising. Okay. Now there is one sort of puzzle that we don't fully understand about this data set, and it turns out that this puzzle is actually everything that the experimentalists plotted in their paper. Okay. So if you look at these curves at low widths, basically the more purple the line is, the lower the width of the device that they measured was, and then the more red, the larger. Okay. If you look at these curves at low width, we would expect that these curves ought to collapse. Okay? So at least mathematically, the Boltzmann equation would tell you that G over W squared is a number, okay? If you're at 0 temperature and there's no impurities. And they don't really see that effect here. They see this kind of weird misordering of the curves, and this is all of the effect that they reported in their paper. Okay? It's all that these curves are misaligned. Now, we were a little bit nervous about that as being the only signature of hydrodynamics. So what we did is we said that suppose that this offset is some experimental artifact. Okay? And suppose that if we just renormalize for this experimental artifact, we can ask, is all of the temperature dependence of this data explained by ohmic scattering? Okay? And we'll assume that there's no viscous effects whatsoever. Okay? So what this model that I'm showing you here is corresponds to a minimal model for the ohmic to ballistic crossover. At low temperatures, we would expect that this term dominates. At high temperatures, okay, this term dominates. And all of this data, quantitatively is perfectly explained by this simple ohmic to ballistic crossover. Okay, the ballistic this temperature dependence to the resistivity is coming from this 60 micron channel, okay, which we think is large enough that we're actually accurately capturing the mean free path. And so what this is telling us is that essentially, in my view, what this is telling us is that there are no hydrodynamic effects in this device. In the end, okay, there's some sort of experimental anomaly, but probably the most compelling explanation for this system is just that it's a very clean metal that's deeply in the ballistic limit at low temperature. Okay, so maybe with that slightly negative point, let me end. So I hope that what you take away from this is that electron hydrodynamics, while people usually think about this subject for systems like graphene, which has a nice, effectively circular Fermi surface, the nature of hydrodynamics, and especially the onset to hydrodynamic behavior, is very sensitive to microscopic details, even in Fermi liquids, which you may have thought would be as close as they could be to a circular Fermi surface. Okay, so even with a hexagon, you can get very dramatic deviations from the sort of conventional lore. And here are some of the effects that I talked about. And then lastly, I think, well, palladium cobaltate is probably not hydrodynamic, but maybe it's still worthwhile to understand better what's going on. All right, thanks.